We really quickly talked about the origin of these names, right? Do I remember that right? Protium because it's literally just a proton. Okay, that's it. Deuterium because there's 2 subatomic particles in the nucleus. Okay, so we get protium and deuterium. So some elements have multiple isotopes. Like I said, everything is an isotope. It just doesn't make sense to refer to certain elements as isotopes if there's only one form of them. Okay, we just refer to them by the element. Okay? Hydrogen is one that has multiple isotopes. There's 2 super common ones, protium and deuterium. Why do we give them their own special name? It's an exceptionally studied system. That's why. Right? That's it. How would that information get translated out for the rest of us? Okay, so one of the things that differentiates these is just the number of neutrons. So you could get a question asking how many neutrons is in a particular isotope. So in this case, we could get the question, how many protons and neutrons does an atom of lead-206 have? That format is a little bit different than our atomic notation, but we talked about that, right? Okay, and what does that format give us information to? We see lead and we have... Okay, we'll come back to that. We have 206 and we have protons and neutrons. Okay, I would argue that protons and neutrons is a more advanced answer to that question. Okay, what is the less advanced answer to that question? Mass number. Okay. Atomic mass got floated out there. No, it is not the atomic mass, okay, which is very confusing because they both say the word mass. They mean different things. We'll address that in a little bit too. Okay, so the 206 is the mass number. Our mass number is the sum of protons and neutrons. So if I tell you lead-206 and I want to know how many neutrons lead-206 has, what else would I need to know? The number of protons. That's going to become a difficult question at this stage because we're missing some information. What do we need to know about lead? We could do atomic number. Okay, where do you find atomic numbers? Periodic table. I'm already really getting irritated at where this periodic table is located. Bother everybody else as much as it bothers me. Where does it say the word lead? Like, I can't see anything. Where does it say the word lead?
82.
Okay. And yes, I'm boxing something in, which is very difficult to do. Do you see the word lead there? No. So what do you have to do before you answer the question? When you see the word lead, you know the abbreviation is PB. Does that make sense? Okay. So we have to have that context. Now that we know that it is PB, now we could reference that on the periodic table. It's kind of funny. That red box means absolutely nothing there. I was like, yeah, that's kind of cool. Okay. Now that we know we're looking at lead, we can figure out its number of protons. How do we figure out the number of protons? We would have to look at the atomic number. Where's the atomic number found? Top right? I thought it was the lower left. Go for it. What do you got? Depends on the context of the formula system that you're looking at. In our atomic notations, where's our atomic number? The bottom left. Okay. On the periodic table, where's our atomic number? Top right. And we would know that. Oh, geez, it's really hard to see on it, doesn't it? They don't give you a key. Oh, well, that sucks. There's no key. Man. You would have to know for this particular periodic table that the atomic number is written in the upper right-hand corner. With that information, we now know that lead has 82 protons. How do we figure out the neutrons? Now we could subtract them, 206 minus 82. Some number greater than 100. 126. Right? 206 minus 82. Someone said 100 and what? 24. Oh. It's a step above me. I didn't do it at all. Okay? When we have 124 neutrons. Make sense? Cool. Okay? There was this reference to an atomic mass. So I'm going to delete everything. Okay? We have the mass number. What was the mass number? Defined. Protons plus neutrons. And then somebody else threw out another word. The atomic mass. Well, the atomic mass is the mass of our atom. Well, what subatomic particles contribute to the mass of our atom? Protons and neutrons. So wouldn't the atomic mass be the same thing as our mass number? They're both the sum of the protons and neutrons, right? Okay, so why is the atomic mass different? The atomic mass takes into consideration isotopes. For an individual element, we have the possibility for there being multiple isotopes. So different combinations of protons and neutrons. What would be the different for those isotopes? The protons or the neutrons?
The neutrons.
The neutrons, because if we change the proton,
It's a different element.
it's a different element. Make sense? Okay, so our atomic mass is an average of our isotopes. Okay? There's a little bit more nuance than that, but it's pretty close. Okay, so let's determine the atomic mass for hydrogen, because we got two isotopes here, right? Yeah? What do you think the atomic mass for hydrogen should be then? That would be 1.5. That was some awfully fast math. What'd you do?
The mass number, or I guess the number of protons and neutrons in the top left corner, 5 by 2.
So we take the mass number for each of our isotopes. For protium, our mass number was 1. The mass number for deuterium? 2. We take an average, what do we do? Divide by 2. And we get 1.5. I'm not rolling that stupid screen back up again. Looking at a periodic table that you have somewhere near you, is that the number for the atomic mass for hydrogen? No. Okay, so why not? Okay, there's an implied percentage in this that we didn't take into consideration. Okay? That weighted percentage needs to be evaluated when we look at our average mass. Okay? So let's take a look at how we would determine that atomic mass. So atomic mass would be the percent of our first isotope times the mass of our first isotope. In this case, it was 1 for hydrogen, plus the percent of the next isotope times the mass of that next isotope, plus the mass of the next isotope. What if there were 3, 4, 5 isotopes? We would have to take into consideration all of them. Okay? So we would do this until we've accounted for all of our possible isotopes, plus on and on and on. Yeah? The mass that we, or the atomic mass that we calculated in blue already did this. Where does it say the percent of our first isotope in blue?
We'd apply equal parts both, so 50%.
If we break down that calculation a little bit, we can start to see these pieces. So let's break that down. I'm going to do fractional algebra nonsense, right? So I'm going to split that and say that this is 1 over 2 plus 2 over 2. Okay? I'm going to say that's actually 1 over 2 times 1 plus 1 over 2 times 2. That 1 is the mass of A. That 2 is the mass of B. I still don't see a percent here. What does percent mean? Out of 100. Per division 100. Okay? So that 1 over 2 needs to be out of 100, right? How would I get it out of 100 but still be 1 over 2? When I took that normal average, if we will, it was already weighted. I assumed that both isotopes were equally occupied. They were exactly 50%. 50 per 100. That's the definition of a percent. Percent. Century meaning 100. Okay? Am I allowed to make that assumption? No. How do we know that assumption was false?
There was no situation given, or there was no previous information given.
They're not evenly distributed 50-50.
If we assume, how do you know they're not evenly distributed 50-50? When we looked up the atomic mass for hydrogen, what was it? 1.01, 1.008, depending on how many significant digits you used. Are those numbers the same as the average mass? No, which means what was flawed within that calculation? These assumptions were false. Okay? So if I'm going to look at an atomic mass, I have to know what those percent abundances are, or those percentages of those isotopes are, so that I can calculate an atomic mass. Kind of makes sense? Okay. So let's play kind of a thought game here. The atomic mass for hydrogen, we've got identified in that lower left-hand corner. Right? 1.01, 1.008, however you want to look at it. Which isotope is more readily available?
Protein.
Why is protium the one there's more abundance of?
Closer to 1.
When we take the average, it is closer to 1 than it is to 2. You don't have to run big calculations, particularly in a multiple choice. You can start to make approximations and say, how does that approximate out? Kind of, sort of? How are you feeling? Is that good? Is that bad? Or is that just silence and you're going to stare at me? Not so good. Okay, let's try a little bit of practice. Okay. So let's take a look at our percentages. Let's take a step backwards. Okay, and let's not look at all the abundant stuff. Okay, a percent is a unitless piece of information. One quantity over a total sample. Why do we multiply by 100? Okay, your percent grade in the class. First exam, you got a 90 out of a possible 100. You got a 0.9 on the exam. That sounds awful. What would you say you got? You got it. Oh, 90 points. Touche. That changes it. We might shift it to 90%, right? How do we get it to saying 90%? I multiply by 100. That allows me to simplify that. That's the point of that 100. Okay? Interestingly enough, that takes my value from being a decimal less than the number 1 to a number larger than 1. Which one can I deal with better? How many of you can count to 90 on your hands? Those of you being like, no, I can't do that. I cap out at 10. Well, then you could say, well, that's 1. Now I could count through 10 again, right? Count through 10 again, right? Tally that up. So we could get up to 90 on our hands. Count to 0.9 on your hands. Yeah, cutting off fingers, not such a great idea. Right? That's a bad system. So we multiply by 100 to get it up to a system that we can actually count whole digits on. Right? Literally whole digits on. Right? Jerks. Okay, so let's look at a percentage. Bronze is an alloy of copper and tin. If a sample of bronze contains 79.2 grams of copper and 10.8 grams of tin, what is the percent copper in the bronze? So what do we have to do? What am I being asked to do?
So yes, 79.2 divided by 2%.
So cool, I'm hearing a string of numbers. So what am I asked to do? Number. Answer my question, not your question.
What is the percentage?
What is the percent pineapples in bronze?
Of copper.
Okay. The percent of copper. Okay. So that would be the amount of copper, right? The amount of copper in what? Okay, we're lazy. BRZ. Would that be a percent? I would have to multiply by 100. So now I go to the question, do I have the amount of copper?
Yes.
Yep, I read through. There's a number, grams, copper associated. I get 79.2 grams of copper. I need to divide it by the amount of bronze. Am I given the amount of bronze? Okay, some people are saying yes, some people are saying no. Okay. Am I explicitly given the amount of bronze? No. Is it implied? Yes. I am told that I have a sample of bronze, and that bronze has these two things in it. So how do I figure it out? 79.2 plus the 10.8. Now what can I do? Victor, what can I do? Now I can do all those numbers and punch it in. Awesome. Okay. So sometimes we'll jump way ahead and I got to crunch numbers. Okay. I want you to slow down a little bit on that. You want to just crunch numbers on an exam? Okay. Show all that process to how you got to that point first. Okay. So now we can punch it into the calculator and we get, we have to do a little bit of math, division, multiplication, 88.0%. I'm that good with math in my head. Okay? Make sense? So there's a percent. Could we make it more difficult? Why not? How much tin is in 100 grams of bronze? What did I just solve for? The percent of copper. What am I now being asked for? Tin. Different things, right? How many things went into the bronze? 2. If 50% of it was copper, what was the other? 50% tin. 88% of it is copper. 12% is tin. Okay? So we can now remove all of that stuff. We've got 100 minus the 88. Gets us 12% tin. Yeah? Is that what we want for an answer? What did we ask for? How much tin is in 100 grams of bronze? This is admittedly a bad question. Why is it a bad question?
You don't know bronze level. Like we don't know how much that bronze that is that we're calculating in the first place.
You're told it's 100 grams of bronze. What's the issue with the question? So I'm not quite sure I'm following. I'm not saying you're wrong, but I'm not following where you're going with that.
It's a sample.
How much in percentage or?
There's no specification on what for the tin. What unit do I want? Okay. We heard a jump out of, I want grams. Why do you think we want grams? Everything else is measured in that. That means your calculation becomes more straightforward and easier, right? Okay. If it's a vague question, make it as easy as humanly possible and beg your teacher to challenge you. Does that make sense? Okay, so in this case, let's call it grams, because I don't want to do anything more complex. What does that 12% tin mean? Okay, so that 12% could mean a couple things. 12 out of 100 times 100, right? What are the units on that 12? Is it a percent anymore? I just said times 100. That's how I got the percent before. The times 100 is already there. What are the units of that 12? It was grams of tin. What's the units on the 100 underneath?
Grams of bronze.
Grams of bronze. Just by writing out the percent, what did we just find? The answer. Why? It's 100 grams. There's my 100 grams. It's already defined in the answer of 12%. Okay? We could also run it how most people will kind of punch this out. Instead of actually looking at the meaning behind those pieces, so say, okay, well, it's 12%, so that's 0.12 times the grams, 100 grams, which is going to get me 12 grams. So you just brute forced the math and said this is how you solve it, that's what the answer is. Or if you just take a second to write down the meaning of what those things are, what else did you find out? The answer just as easily. Kinda? Okay. So let's make it really hard. This is our simple and weighted averages. Okay? Our weighted average is calculated by multiplying the percent, okay, by the weight of the object, okay, for each object, and then adding them all together. Okay? That's a challenging thing to look through. That's the formula that I'd actually already written up. Okay, so I want to rewrite that formula, and because I think language can sometimes be confusing, let's look at that formula. We said the percent of our first isotope times the mass of that isotope plus the percent of the next isotope times the mass of that isotope. Okay, and we do that so on and so forth, and what does that end up equaling? The atomic mass. Okay? So there's kind of our formula system that we're working with. That formula that we derived literally out of just doing averages. Okay? Gallium has two isotopes, 69 with that weird mass number with a 60.11% abundance. Gallium-71 with the mass, or what is the mass of gallium-71 in that weird unit system with 4 significant digits. Okay? What information does the question give us? Okay? Gives us a mass number. It's a little bit shaky because when we think about mass numbers, we think our mass number should be whole numbers. It's the number of protons and neutrons. This is an actual mass of that isotope. You'll notice it's very close to whole numbers. Why is it not exactly whole numbers? It's how we quantify that weird mass unit, that AMU. Do you need to know what that AMU is? No. Don't worry about it. Okay? It could be pineapples for all we care. We just have to make sure we maintain that unit system. So we have a mass value. Okay? We have that mass given for us. Okay, that is one of our effective mass numbers. Which one? Massa A, massa B? Okay. Massa A. Who says massa A? Who says massa B? Or is it a trick question?
Good question.
It's a trick question. Why?
This is below both of these numbers too.
Nope.
Doesn't matter which one
It doesn't matter which one it
it is.
is as long as you pick and you're consistent behind it. So if you're going to define A to be 69 gallium, then that mass value that was just given is the mass of A. If you define A to be gallium 71, do you have the mass of A? No. Okay. So what we're trying to do is take this mass of letters and numbers and simplify them into some other form so that we can calculate a little more easily. Okay? So let's take a look at what we've got. A for gallium 69. Do we have the mass of A? Yeah, what is it? We'll throw in that AMU. Do we have the percent of A? Yeah, that's also there. Cool. Okay, what do we know about B? I did hear what you said, but I'm going to disagree with you for a second. What's the first thing that we might want to write down? So there was a suggestion for a percent. I don't think we should write down a percent first. What should we write down for B? And I have a feeling I know why you're balking. I think what we should write down would be the mass of B. Why might you balk at me saying, let's write down the mass of B? That's what you're looking for. You don't know what that is. That's okay. Put a question mark. Put an X. Why should we put the mass of B first? It matches the alignment of the rest of our work. The more consistent we can be in that process, the less likely we'll make mistakes. Simple. Simple change. What's the next thing we should address? The percent of B. Okay. For those, we'll just try it anyway. Does the question tell you the percent of B? No. Do you know the percent of B? Yes. Okay. How do you know the percent of B if the question does not tell you the percent of B?
Abundance. This is the 60.11% abundance and the gallium 71. Would those be the same?
The 60.1, so that's where we have to be careful on reading our sentence. Gallium 69 with a mass of and 60.11 abundance. Effectively, there's a comma there. That 60.11 abundance is going to tie to the previously stated statement, which would be our gallium 69. The gallium 71, we've got nothing on. Rest of what percentage? What's our total percentage?
100%.
100%. I know 60% of it, ballpark, is A. How do I know the rest of it is B? There's only 2 isotopes. Which means if I know through this system that the percent of A plus the percent of B must equal 100%. Do I know the percent of A? Yep. So how do I figure out B? 100 minus the 60.11. I lied about being good at math. Okay. How are we doing? Do we have the answer yet? No. We could start to throw numbers up at an equation. Whoops. So, percent of A, do we have that one? Yeah. It was 60.11%. When it goes into the equation, we can't put it as a percent, but we'll write it out to represent that. So it'll 60.11. It's really small. That's bothering me. Over 100, right? Percent. So far, so good? What is the mass of A? Do we know the percent of B? You just solved it, right? Cool. This is actually looking pretty good. We've got the majority of our stuff in here. Do we have the mass of B? No, that was a question mark. Do we put question marks in expressions? No. What do we typically put in if we don't know it? Variable. What variable do you want to pick? B? Okay. It's fine with me. That works. B. What does this then equal? Okay. You know what I get a lot of people doing? Or those people being like, where did 1 come from? Exactly. I have no clue where you're getting 1 from. No, that does not equal 1. What does it equal? The atomic mass. Was the atomic mass given? Well, if it's not given, we must not be able to solve. Do you have a periodic table? What is the mass given on the periodic table? Generally, it would be the atomic mass. Which means, what do you need to do? Pull out your periodic table and find out the atomic mass for gallium is
69.72.
Now what do? Now you can do all the algebra and fun stuff to figure out B. Yeah? Questions? Remember, I can't do math in my head. I'm more than happy to sit down and punch into a calculator all the algebra behind that to work through that with you. Okay? I would kind of like to not do that right now. We okay with that? At least one student has pulled out a calculator, which I think means to me she wants a number. That's cool. Your calculator literally just die. Okay, there's a couple other people with calculators. Let's spit out a number. What do we get for B? Because a couple people are doing it. 70.9165? Okay. We get a second? Anybody else running it? I want to pause the video here for a second. Running that calculation. Does that number make sense? Gallium-69 had a mass of what? 68.926. So darn close, right? But a little bit under. Right? What do you think the mass for B should be? Darn close to 71, right? But a little bit under. Ballpark, that looks reasonable. Did we get a second yet? Are we getting different numbers? What'd you get? Same number. So we've got a second. 70.9165. Okay? A vast majority of you watch the play posit on significant digits. Okay? Don't stress about significant digits in this unit. But fix that number. I want 4 significant digits. And the answer becomes how are we feeling? A little better? Okay. I don't like math, so let's get away from it. Periodic table. So we're going to do a big jump here. We read half of chapter 4, and now we're going to fly into chapter 5 and see what's going on there. Chapter 5 is all about the periodic table. What do you see up on the board?
An acid trip.
An acid trip, that works. Those are periodic tables. Okay? Do those periodic tables hold the same information that the periodic table under the freaking whiteboard or under the projector screen holds? Mix and mash? Maybe, probably. Why are they formatted differently? we're trying to pull different information. For the really weird acid trippy looking one, the size of the symbol is representing the abundance. Hydrogen is huge, oxygen is huge because
It's very abundant.
we got a lot of it. You go through and look at all the other ones, they're relatively small. Why?
Rare.
They're not abundant. Okay? They're very rare. So we're embedding information in different ways. The circle one and this weird diagonal triangle thing, okay, also hold information, and they're there allowing you to pull access to it in different forms. So somebody looked at it and said, it's better to organize it this way because I can get access to this information faster. Okay? So you may see different forms of the periodic table. They all have slightly different nuances. Some of that comes with experience. For the most part, the periodic table that we are going to study will be the one that's behind the whiteboard. It's really irritating. I'm going to put in a work order. Let's get a real one. So, how was that periodic table organized? Okay, we looked at Dalton, and we saw Dalton's periodic table with just pretty pictures and all over the place and not really well organized. Okay, maybe 20 years later, don't stress about the scientists' names or dates. Okay, Dob Reiner looked at it, and he says, actually, even if you look at Dalton's, it looks like we could get sets of 3. Okay? Well, 3 is a really important number. Why is 3 a really important number? H2O, okay, way to think like a scientist. Father, Son, Holy Spirit. 3 is a very important number when it comes to religion. We've seen sets of 3s in lots of places. Dobberner's like, I just cracked the code to all life and God and everything. Everybody's awesome now. Look at science. Okay, so we looked for those patterns. Okay? So we saw very similar chemical properties, and that's how we decided to organize them. You're looking in 30 plus years later, Newlands suggests that the 62 elements need to be arranged differently. We now have a lot more elements. They don't work as sets of 3 anymore. But what he does notice is they work actually as sets of 7, okay? Which is interesting. Okay? When you look at those sets of 7, it looks kind of familiar. It looks kind of like the law of octaves. Where have you heard of an octave before? In music, where you go through 7 notes and then you cycle, right? Musicians have told me that's true. Okay? The law of octaves. Well, he's like music and science. They meet the same thing. Look at those patterns. Okay? So we're still trying to find those patterns and force patterns on what we're studying. Okay? So this is something that we do as humans across the board. Okay? So it's kind of neat that we were seeing these patterns and what was going on with it. That law of octaves didn't end up holding, and we end up getting Mendeleev going through and playing with these organizational patterns. Mendeleev, notice his name is in red, is incredibly important because he's the one that we give a lot of credit to. Okay? His final organization became so cool that we said, okay, Mendeleev's the father of the periodic table. Okay? Why was his periodic table so cool? What do you see when you look at that periodic table? Anything stand out as kind of interesting or bizarre? It looks kind of similar to ours. Right? We started with hydrogen, lithium, beryllium, boron. That looks pretty similar.
The organizing columns.
We get columns. Relatively simple. There aren't a lot of elements, so we don't have a whole lot of things to discover. What other things do you see in there? What do you see? What do you mean? Where do you see those predictions? There are some spaces. Those spaces are like, I don't really know what's going on. There's something weird there. But more importantly, are not the spaces, but the ekas. Those ekas weren't just spaces. That was him going, the rest of you experimental scientists out there, because Mendeleev just kind of sat back and studied stuff. Okay? The rest of you experimental scientists have screwed up because you didn't find an element. It's out there. Go find it. Okay? That's kind of crazy. That's why his periodic table is given so much credence, because he was able to organize it in such a way that he could see gaps and predict future elements. That's cool. Okay? So let's take a look at some of those guesses. 1869 is when he predicted this new element. 20 years later-ish, we actually get the element discovered. Okay, so if I came to you right now and said, in 20 years, you're going to have gray hair. You're like, screw off. That's a piss poor calculation. Okay? Atomic mass. You will weigh, and I give you a weight. Okay? Not only do I give you a weight, but I will say your density. Your body mass percentage will be this. 20 years from now. What would you tell me? I'm freaking crazy. There's no way that's true. Color, yeah, gray. Whoop-de-doo. Look at the metals, number one. They're all freaking gray. Way to predict, dude. Atomic mass, 72, 72.6. Okay. Density, your body fat percentage, 55 or 5.5, 5.32. Okay? Melting point. Your temper is going to change a little bit. You aren't going to be super angry all the time, or you're going to get more angry. Okay? Predicting temperatures. Admittedly, very high isn't very specific, but come on, 937 degrees is pretty dang high. Okay? Now the fun ones. The formula of the oxide. In 20 years, now that I'm going to tell you all this, I'm going to tell you stuff about your kids. Okay? Who you married. What did they react with? Look at the parallels between these things. That's pretty freaking amazing. Okay? That's why we give Mendeleev so much credit. He was able to not only organize the patterns, but then be able to predict these massive properties. That's cool. Okay? That's why we recognize Mendeleev's ability. Yes?
How was he ever able to do that?
Because he could see the patterns behind how the periodic table was organized. Okay? Which is extra fun, because if we look at those timelines, okay, we talked about atomic theory, right? When did we discover the electron and the proton and the nucleus? He discovered ecosilicon in 1870. Proton, neutron, nucleus? 1900, 30 years later. We don't even know about subatomic particles, and he's able to make these predictions accurately. He also made a lot of wrong predictions. But everybody remembers the right ones. Okay? He's also a very weird, crazy dude. I recommend studying him if you're interested in finding out about scientists, because he is a very weird, crazy dude. Okay? To the question of how was he able to do this, he slept and he dreamt it. Were we talking about acid trips earlier, right? Okay. If we continue through our science on this, we come across our noble gases and nuclear charge. So the periodic table gets expanded and adjusted a little bit when we find noble gases. Okay. Why did we have to wait to find them? Well, if someone was in the nobility, do you think they would be in this room? Some of you are like, yeah, you're not a bad teacher. Thank you. I appreciate that. But be honest. Okay, if someone was in the nobility, they aren't in this room. Okay, they're going to go somewhere else where they can buy their way in and buy their education. Okay, you guys have to work for it. Okay, the nobility doesn't interact with the rest of the world. The noble gases are pretty much the same thing. They don't interact with things. Not only that, they're gases, so they're harder to work with. They're harder to track. Okay, so it took a very long time until we could actually identify the noble gases. Okay. That discovery is largely due to Ramsey. Okay. When we get further on into the 1900s, when we actually start pushing into what makes up the nucleus and nuclear charge, that's when we actually notice the periodic table has some weird exceptions to the trends that Mendeleev picked. Because the trends that Mendeleev picked were based off of mass. Okay, why did he pick mass? Because he didn't know what a subatomic particle was. After 1913, Moseley comes along and goes, actually, those weird oddities that Mendeleev kind of screwed up on, if you just do a slight switch and not look at mass, but look at the nuclear charge, everything fits perfectly. Okay? So what that is, or what that becomes known as, is the periodic law. So our periodic law is that our elements recur in repeating patterns when they are organized according to a increasing atomic number. Atomic number is our number of protons. When we look at the periodic table, what's typically the first number we see for any individual element? The atomic number. Why? We're trying to match periodic law. That's why we get a shift away from atomic notation. Okay? So we now have our periodic law. Okay? The ultimate organization behind this gets solidified once we understand a little bit more about electrons, which hopefully we'll get to today, but we'll see what happens. Okay? So, groups, periods, for our periodic table. We get groups and periods. Our vertical column is known as a group or a family. Okay? Most people within a family have similar habits or patterns. Same thing happens on the periodic table. Okay? So if I know how lithium interacts with oxygen, I also know how potassium interacts with oxygen. Okay? So that's kind of cool. So it's helpful to identify those groups and families. The horizontal row is known as a period or a series. Okay? You are responsible for knowing what those terms are. Okay? And you can see that when you go ahead and look at the practice exam. Certain columns get extra names. Why? Because we just like naming things. Okay? So the first column gets called the alkali metals, okay, which happens because, if we ignore the word metal, because everything to the left of that staircase was a metal, right? Yes, cool. If we ignore the word metal, how many words are there? One, alkali. Which column is it? The first column. Hey, that's kind of cool. What's the next column? Alkaline earth. If we ignore the word metal, how many words? Two, second column. Always got alkali and alkaline earth confused with each other. Now I don't. Alkali is the first column, alkaline earth is the second. Okay? When we talk about stupid things to help us remember things, that's one of my stupid things. Okay? After that, we can see the transition elements in that kind of pale green through the middle. Okay? And we will come up with other names for those. So there's our pale green. We will talk about what this section is as a whole a little bit later, but we will reference our noble gases as the yellow part of that. Okay? So that last column. And then you will also hear reference to halogens. Okay, as our fluorine, chlorine, bromine, iodine. Okay? So we're responsible for knowing those names. I could ask, which of the following is a halogen? And give you a list of names. You would have to be able to piece that out. Make sense? Should hopefully be relatively straightforward. Okay? I like to throw in some of those common names just because I think they're interesting. Group 15, the pnictogens. It starts with nitrogen. I just think that's fun, right? Pnictogen. Somebody laughed. You can say it with me. Pnictogen. It's kind of fun, isn't it, for the two people that said it with me? Okay. The other one, 16 with oxygen, is the chalcogens, which I'm pretty sure I butchered the pronunciation on. So it's also kind of fun just because I screw it up so badly. Okay. You're not responsible for those, but you might hear reference to those. Okay. Sometimes in Greek and Latin roots for more advanced names. Okay? So, this slide is a little weird. I thought it was a little bit earlier, but it's shifted way late. Okay? So let's take a look at a question that we could be asked. Okay? What we're trying to do is act like Mendeleev. Oh, who's coming in that back door? Oh, never mind. I don't know what that was. Given the above information, what is a reasonable density for potassium? So the first thing, is there a lot of information up there? Yeah, we should probably get some selective vision going on here. What's that selective vision need to be? I just need to see the density. I don't care about the radius. I don't care about the melting point. I don't care about the atomic mass. Right? So I'll selective vision that stuff away. Okay, the next part, I want for potassium. What does potassium have to do with any of those elements? Those of you with a periodic table in front of you might be able to figure that out if you memorize the symbol for potassium. Potassium is K, And K is found where in the periodic table? In the alkali metals. Group 1, period 4, underneath sodium, which was underneath lithium. Potassium was above rubidium, above cesium. That giant gray box is our potassium. Okay? So we can now look at the densities. What happens as we move down that column to our densities? They get more dense. Okay? So what would be a reasonable guess for potassium? Okay, 1.2, 1.3. Anybody else want to volunteer anything else? 0.7? No, why not? That doesn't match that pattern, right? It would be going backwards. Did everybody catch that and see that? Okay. So, multiple choice question. Which of the following... Who's coming through that door again? Given the above information, what was a reasonable density for potassium? B. Okay. For those of you that kind of laughed, it looks like maybe you saw what was going on there. We could say B was our reasonable density information. That's the stuff that we have at hand. Okay? If we erase or remove that white stuff, or remove that gray bar, what do we get? What was the density for potassium? What did we guess? What do you think? Is B still the correct answer? B is the correct answer still because that was the information we had at hand. Okay? It does not have to be true. Okay? That is a challenging concept to deal with. What you should be focusing on is learning. How do we adjust from this? We've come up with a theory. That theory was tested and proven wrong. Irrelevant. We had a solid theory explanation behind that. Okay? This is the first class that has been like, yep, that's okay. You're really all like, yeah, that makes sense. I totally understand with you. Okay. For those of you who might be saying no, feel free to talk to me after class. Okay? But that is what I want you to be able to do. I want you to be able to look at the data at hand and be able to make a guess. That guess does not have to be 100% correct, but it has to be supported by the evidence that you've seen. Okay? So, chemical properties. All of the alkali metals have oxides in the general form M2O. What is M? Metal, because these are the metals. Okay? So if I'm looking at an alkali metal, for instance, lithium, sodium, potassium, rubidium, cesium, or francium, when they react with oxygen, they form a new compound. In that new compound, there will be 2 metals and 1 oxygen every single time. Okay? This is what it means to be in the family. You have that same reactivity. So we can now predict things based off of limited information. That's kind of cool. Okay? We can also see with it images. If we throw lithium into water, okay, we get this kind of little blurry thing. What happens if we move to potassium? You get effectively the same thing. Maybe a little bit bigger, but in potassium's defense or sodium's defense, it is a little bigger. Potassium, largely the same thing. Rubidium is starting to cause some problems, and cesium literally just made a mess of everything. Okay? But the chemistry is the same. The scale at which it happens may change, but we're getting the same basic patterns all the way through. Kind of make sense? Okay, so that's kind of cool. Okay? How could I ask an exam question about this? That's a much harder question. Okay, so what I'll switch it up to is say, I want when aluminum This is a lot easier if I had a periodic table. When aluminum reacts with, we'll make it a little more straightforward, with chlorine. So what am I asking? Which of those is the correct answer? Okay. There's a little bit of confidence in the back. You guys ready for it? Here's what it was.
None of these.
Good answer. There's not enough context yet. Okay, we need some more information. That more information has to do about knowing where aluminum and chlorine are in their respective families. Okay? So what I will also provide not going to provide that one. Gotta think of these kind of on the fly, which makes it a little bit different. Oh, I'm just going to butcher them. Why not? Yeah, we're just going to make them ugly and non-existent. Oh well, we're there. And so a couple people were shaking their head vigorously. Does that change it? That is now part of the given information. Like, nope, that doesn't change anything. Okay? It does change some stuff. What does it change? Okay, those are how those metals all react with chlorine. Okay, so we're seeing some commonalities there. Okay, what else do we see? Well, that would be matching patterns, right? Of course, I didn't do such a great job aligning these. There's a matching pattern. There's a matching pattern. This pattern wasn't matched in any of the given information. This pattern didn't match anything in the answers. Right? So if you guess B, what context would ever lead you to B? Nothing. Okay, so that's a pretty questionable answer. Okay, what is the relationship between silicon and aluminum? Same period. So somebody has a periodic table in front of them. Does everybody have a periodic table in front of them? Yeah, okay, good. That's probably a good thing to have in front of you, at least until we get the board up. They're in the same period. Do chemicals or atoms in the same period react the same? No. Okay, so A is not looking so good. What about C? S, sulfur versus aluminum. Where are they? Same period again. So if we're going to say no to silicon, we should also say no to sulfur. How about the last one? Gallium's in the same column, also known as the same family. Families react similarly. What's your answer? D. Make sense? Notice the given information, particularly if I had done it correctly, matches all of the potential outputs for the answer. Everybody see that? Should have been done better. Okay? That means the multiple choice question requires that you know something so that you can make those parallels. Yeah? If you don't know those parallels, you are blindly guessing. For those people being like, well, I just see the answer, that one makes sense, you're literally just guessing. Even when it comes to a calculation, you get a number at the end, the calculator gives you a number. You're like, oh, 2. 2 also shows up in the answer choices. It must be right. No. Some smart aleck instructor went through and said, what is the most common way students are going to screw this up? What answer would they get? 2? That's one of my answer choices. A properly written multiple choice question says that every possible answer has a decent output. Okay? You need to know the content. Okay? Periodic trends. This is a fun one. Okay? You all read about periodic trends, right? Okay, cool. We can look at the size of the atom. So when I ask size, what is being measured? Okay, the radius. Which subatomic particle is responsible for the size? The electrons and the electrons alone. I don't care about the protons and the neutrons because the protons and the neutrons are in the nucleus, a marble inside the superdome. Okay, so when we think about size, we may think about weight or height. When it comes to atoms, our size is the equivalent of just the height, the radius. I don't care about mass. Make sense? Okay. There are two trends for atomic radii. What do you think those trends are going to reference? We looked at a periodic table. We had the period, which was our row, and the column or groups and families, right? That's two directions. Okay, I can go down or I can go left to right. When we're talking about trends, those are the two trends. What happens to the size of the atom when we go left to right or top to bottom? Right? Anybody want to venture a guess? Which is smaller? Okay, for which one? Top to bottom, left to right? Top to bottom, it gets smaller. Okay? The suggestion was smaller. What does it mean to get smaller? What contributed to size? Electrons. What happens as you go down a column? You add electrons. Does it make sense to get smaller? No, it does not. Okay, this is why knowing where size is coming from is important. When we go down a column, what happens? It gets bigger. Why? More electrons. What happens to size when we go it's the left side to the right? It gets smaller. Okay, so if it's getting smaller, it must have less electrons, right? Left to right, it still gets more electrons. The rule we use to explain down a column now conflicts with the rule we use to explain left to right across a period. That's a little weird. Okay, is it true? Yes. Okay, so those are the valid trends. Left to right, it gets smaller. Bottom to top, it gets smaller. The question becomes why? Okay? That why question is a difficult question to answer, particularly at this stage, because what we're asking with that why has to do with our electrons. Where do the electrons exist? Outside the atom. Where outside the atom? For instance, would you still look at me the same way if I was wearing my underwear outside my pants? You just look at me and say, oh, wow. It's mildly insulting. Okay? We get a different response. Those electrons aren't just outside. There's an order behind that. Have we discussed that order? No. At this point in the game, we haven't addressed anything about the order of where the electrons are, which means explaining these trends is very, very difficult. We need to understand where electrons exist before we can really understand these trends. Okay? So the first thing we'll do is, again, address a prettier picture that shows those trends. Okay? So you can now see them. These are trends, not rules. Okay? So that is a difficult thing for people to process because you go through, a trend, that means it's always this. And I have to memorize an exception. It's not always this. Okay? And you don't have to memorize an exception either. What I want you to know is the trend. Okay? Yes, there are exceptions. I don't care. Basic trends. Okay? So now what we want to know is why. What's going on with this? Well, to address that why, what are we going to have to learn about? structure of what? Where the electron structure exists. Okay? So we could look at another picture for radius and metallic character. That would be a good thing to draw on a periodic table, say for an exam. But what we're going to do is bounce back to chapter 4. And we're going to look in the second half of chapter 4, which is now addressing where our electrons exist. Okay? To do that, we have to understand a little bit about light. Okay? There's a bunch of facts up here about light. We got wavelength, which is the distance between two peaks. We get frequency. For an arbitrary distance, how many peaks went through? Okay? We put all that information together, we can come up with an equation, energy. Okay? Planck's constant times the frequency. Anybody heard of Planck's constant? Okay, like 3 people. Does anybody want to work with Planck's constant as a calculation? Okay, like 1 person. Take 151. The rest of you, just not worry about it. I don't want to deal with it. Okay, so we don't have to deal with those calculations. All I want you to do is be able to identify what a wavelength is, a frequency, okay? And that's actually it. Okay? So when we think about light, what is light? Light is part of the radiant energy spectrum that was formerly known as the electromagnetic spectrum. Why did we switch to the radiant energy spectrum? It's less scary. You're like, that's crap, that's not true. Anybody had an MRI? Yeah. It's actually an NMRI. What's the N? Nuclear. You mean you climbed into a nuclear bomb to get an MRI? No. But that word nuclear in front meant nobody got inside one. So they dropped it and just called it an MRI, and everybody takes them now. Okay. Careful. Okay. So when we're going through and looking at this, our radiant energy spectrum spans a big range. We get cosmic rays, massive, massive energy particles or energy rays, all the way down to radio waves. Okay, that's our electromagnetic spectrum. Visible makes up a very tiny little piece inside it. Okay, so what I want you to know is what are the colors in the visible range? What are those colors? Blue, green, red, okay. Violet. Okay, just for the record, if we look at this, we heard blue. We heard green, okay. We heard red. Hey, look at that. We're moving all in one direction. Oh, wait, violet now over here. Orange. Okay, so you're jumping all over hell and gone when you list these out, guys. That makes it difficult to rank them, right? Might be nice if you had a nice, consistent pattern that you could follow. Roy G. Biv. Red, orange, yellow. Hey, Roy. Middle name G. Last name Biv. Red, orange, yellow, green, blue, indigo, violet. Works out pretty well. Okay, you now have them in sequence. You'll notice that is in kind of the opposite sequence written there. That's not a huge issue because the next thing we need to do is layer on the next piece, the energy associated with these, because that's important to me. Okay? Which is the highest energy? Okay? It can be easy to confuse. Okay? Particularly because as you look at that, the red one gets this big old wavy thing that looks scary, and the other one's all this tiny little, like, I don't care about that tiny little stuff. The big stuff, that's scary. Okay? It's the other way around. Okay, so how can we make sure to remember that? We step outside in Arizona in the middle of the summer and we protect ourselves. Why? We protect ourselves from sun rays. And what part of the sun ray are we protecting ourselves from? The UV rays, the ultraviolet rays. Why are we protecting ourselves from the ultraviolet? Because that can damage us. That is high energy stuff. Which one is closer to ultraviolet? Violet or red? Violet. Ta-da! There we go. High energy. Just from walking outside. Okay? That necessarily means that our red is going to be low energy. Okay? Neat. We've now got those pieces kind of nailed down. How badly do I want to keep going? Sure. We'll finish on this one. Emission line spectrum. Okay? So, we've got light, we've got all these energies, and now we start playing with our stuff. Okay? Why not? We just got tubes that we could evacuate all of the material from, and we could put in whatever we wanted into these tubes. So I'm going to take that tube that was a vacuum, and I'm going to pump hydrogen into it. Why? Because I can. Okay? Not only can I, but I think it is exciting because, you know, I'm an older brother, and I thought it was cool to make my brother stick a fork in the electrical outlet. Okay? Because it was neat. So I'm going to do the same thing to this tube of gas. And I'm going to pump 20,000 volts through it. I didn't do that to my brother, for the record. Okay? When I did, what happened? It glowed. Pump 20,000 volts into you, you glow too. Okay? But it glowed. And we got this weird purple color. Okay? Because we'd already played with light before, we'd seen rainbows, we knew prisms. We passed that purple light through a prism. Because it was purple, what did we expect to see at the other end of the prism? Bunch purple light. And what we saw instead was not just a band of purple light, but I saw very distinct lines. I saw a purple line, a blue-green line, and a red line. Not these big, expansive sections of just purple light, but very distinct lines. That's kind of weird. That 20,000 volts, what was that 20,000 volts moving? Electrons. So when I pumped this in, the output that I'm getting is probably due to the electrons. The electrons are doing something weird here. The electrons can only exist at very particular energies. That's interesting. Plum pudding model said everything exists everywhere. Rutherford says put them in the nucleus, protons and neutrons, electrons exist everywhere. 20,000 volts through a tube of an element, they exist at very distinct locations. That's interesting. All right? We'll pick up there on Tuesday.